Okay, I think we'll get going here. So, hello everybody, welcome. Thanks for coming. It's my pleasure to introduce everybody to Mason Kadem today. And in his talk, he's going to be sharing a few work streams that highlight the importance of transparent AI in healthcare, both in clinical and research applications. Mason co-founded Research Online and is currently building infrastructure for large-scale health research online. Mason holds dual master's degrees in neuroscience from Western and biomedical engineering from McMaster, with machine learning training from the University of Oxford. His background combines interpretable machine learning, technology, data science, cognitive science, biochemistry, physiology, imaging, and business to drive research innovations. He authored the textbook Pearls and Perils of Machine Learning, which is used in multiple academic courses. Moreover, he holds positions as a college professor and head of AI at McMaster's Translational Vascular AI Lab. So, Mason, take it away.
Thanks for that introduction. I am very excited to present these work streams today. And by the end of this talk, I hope that I can elucidate or clarify that perhaps the future of responsible medical AI lies in inherently interpretable models rather than trying to explain complex ones, especially in medicine and particularly in high stakes decision making, like in the diagnosis and prognosis of disease. The first work stream that I'll present is on Alzheimer's disease. Alzheimer's has caused an enormous economic and human burden. And easily interpretable, accurate, and accessible prediction tools for early AD do not exist. And despite the power of machine learning, and especially these gradient boosted ensembles, which I'll talk about, which outperform deep learning in performance and interpretability, their complex structure still limits their clinical utility and generalizability. Our objective here with this first study was to leverage a large multi-site data set, over 57 sites across the US and Canada, and state-of-the-art supervised machine learning. And we wanted to support AD healthcare decision-making and planning, and potentially reduce this burden of AD, and more generally, to improve the adoption and trust of machine learning models in medicine. And our question here was, can we create a highly accurate yet clinically functional prediction tool for Alzheimer's disease that is rapid, non-invasive, accessible, and cost-effective? When looking at the literature for prediction models, and it doesn't necessarily need to be for AD, you can replace that with any disease. There are many limitations with existing prediction models, namely that models are developed using traditional statistical methods, which overlook nonlinear relationships and complex interactions between features. Now, I'm going to come back to the slide in a second, but I thought for the audience, I wanted to give a general overview between traditional statistics and machine learning. Appreciating that this isn't by all means clear cut, I just wanted us to appreciate that both these domains grew up independently. And there is a lot of overlap. So for example, when I talk about relevant features, selecting our variables, in traditional statistics, we rely a lot on domain expertise. But we do that too in machine learning. But again, more emphasis on feature selection algorithms. When we talk about data size, modern statistics has no problem handling larger data. And when we talk about larger data in machine learning, we assume that you have the infrastructure to handle it. Again, interpretability, generally high in traditional statistics, but I'll be talking about interpretability in machine learning today. So it's just important to appreciate the differences and the similarities between these two fields. Now, going back to the limitations, a lot of machine learning based or AI models in healthcare solutions use features or variables that are difficult to acquire, invasive, manually selected, and costly, which limits the availability of these variables and their usage. And I'll show later on, while identifying high-risk factors is certainly important, we have ways using interpretable machine learning to actually get absolute threshold cutoff values for these variables, which would further aid in the understanding of the decision process. Finally, machine learning models often lack interpretability. Although explainability and interpretability are often used interchangeably in the machine learning field, herein, I'd like to differentiate those two terms. Explainability will refer to providing accessible explanations to end users for complex models, like Shapley values, whereas interpretable models are understandable by design, like decision trees. And I think this is the most important part that I'll say today. And really, the clinical adoption and end user trust of machine learning models necessitates understanding of the decision process. But again, the complexity of machine learning algorithms hinders the formation of clinically quantifiable explanations of that process, which impedes their adoption. Now, the next few slides, I'll empirically and theoretically motivate the use of inherently interpretable models that can also maintain performance with their complex counterparts. This was a fascinating study, Nature Machine Intelligence. Here they compared these gradient boosted ensembles, which are an amalgamation of decision trees. And decision trees are just hierarchically organized binary classifiers. And when you amalgamate them in parallel or series, they become quite powerful, yet interpretable. And here they compared gradient boosted ensembles with linear models and neural networks, showing that gradient boosted models are outperforming these other models. But I do want you to ignore the panel. I think these values are the same or similar. So I do want you to ignore this first panel, and I want to draw your attention to panel B. And they did something fascinating here. They increased the non-linearity in the data. And if we think about AI in healthcare, we really need to consider the nature of clinical data, non-imaging clinical data. And age with any health condition is often nonlinear. Blood pressure, treatment dosage, genetic factors, physical activity, biomarkers from blood glucose to hormone concentrations, nonlinear. And so when you increase the non-linearity in the data and you're comparing gradient boosted ensembles with a linear model like logistic regression, you see a decrease in performance with a logistic regression model. And this makes sense. You have a mismatch between the data generating process and the model. And of course, we appreciate the bias and variance trade-off when it comes to performance, but it's less appreciated when it comes to interpretability. What's pretty scary here is that in these linear models that are abundant in medicine, is that something like logistic regression, as you increase the non-linearity in the data, it starts putting irrelevant weight or putting weight on, irrelevant features as you increase the non-linearity in the data. The take home from this slide is that these gradient boosted ensembles can be more trustworthy, higher performing, and more interpretable than these linear models. Moving on to more empirical evidence of these boosted trees. I apologize, this is a bit small here, but I find that a lot of folks that are taking up machine learning sometimes just throw every model at the problem and hope something sticks. And this is a form of p-hacking. So what I'm trying to do here is empirically and theoretically motivate the models. We're seeing here for non-imaging clinical data, so heterogeneous tabular data, these gradient boosted ensembles outperform every other model, including all the other deep learning models. This is another example. One of the largest studies done, 150 data sets around that. And again, we're seeing these gradient boosted ensembles and their derivatives outperforming the rest of the models. Now, we can also theoretically motivate these models, and especially when we think about deployments and how these models scale. And we want to ensure validation that your model, great, that it works in a certain scenario. We want to make sure that it generalizes to a real world setting. And linear models, I'm downplaying them a lot here, but they have their uses for sure. But the problem here is that linear models plateau with large samples. Decision trees are prone to overfitting. They can fit the training data to death. And the point here is that these random forest and XGBoost models, these gradient boosted ensembles, do a great job of balancing the bias and variance. And I would argue here that XGBoost does this a bit better because the random forest process creates these homogeneous trees in contrast to XGBoost's heterogeneous trees. And XGBoost has the explicit regularization in it to improve generalization. Okay, So hopefully we've motivated these gradient boosted ensembles for a problem. I want to remind the audience that we are not using any imaging data here, and it's just tabular data, neuropsychological testing, brain volumes from MRI that are extracted, genetic data, lifestyle, and health history, heterogeneous tabular data. And this is a binary classification problem. Now, the machine learning process here, we want to ensure stability in our feature selection. The point here is not to just focus on performance, right? We want to focus on clinical adoption of machine learning models. So we want to get into a simpler model and a lower dimensional data set. And one way to do this is to, here, this is 100 round random splits, 7-3 splits, XGBoost training. And here we use the gain feature. And this is quite important because a lot of feature selection methods only kind of focus on the presence of a feature in the model. But here, the gain is the proportionate split-induced contribution to the model computed for each tree in the model, which accumulates the presence and contribution of each feature. And we do this 100 times for feature stability, and then identify top selected features. I do this for this project, but you'll see later on that this is actually quite problematic. When you have a subset of features and you're just kind of picking the top features, and even in traditional stats where you use domain expertise to, let's say, pick 10 important features out of your data set. So this runs into a lot of issues later on. Now, this two-stage feature selection process, you start by identifying, let's say, the top 10 features out of 50 features or more. After that, you can select the top feature. And again, for performance stability, we can do 100-round 5-fold cross-validation for our performance metric, and only add the second feature if it improves performance. And then we get to this minimal feature set. And this is how it performs. So you see that the first feature was quite high at 94%, then 96, then 97. And as soon as we see no improvement, we stop taking the features, right? I want to highlight that the prior feature selection method that I just showed used the full ensemble of booster trees. These are 150 trees that are working in concert to correct the errors of the previous tree. And they captured the complex interactions and nonlinear relationships, enabling this identification of a highly predictive yet a minimal feature set for a more interpretable model that I'll show later on. Looking at the distributions, we see that for most of these distributions, they're quite divisive. This is what we want to see. I love these pair plots. I highly recommend if you're doing a binary classification problem with tabular data, this is probably your go-to plot to assess the distributions. And then we take these features that are quite divisive and then constrain the XGBoost model and its hyperparameters. So the nice part, sometimes you don't work with a lot of data. And again, you can theoretically motivate your model such that you don't have to do cross-validation for your model, but you can also theoretically motivate your hyperparameters. So here, I constrain the XGBoost model to a single tree. I remove the explicit regularization and the subsampling of rows and columns that was very useful for the feature selection. And then the point here is that we want XGBoost to have access to all the features and training data. And then you end up with something like this. And it's a high-performing model, and it's a data-driven model. This is it has no human bias, and this is as interpretable as it gets. And I argue that this is, I think, the immediate next step for AI-human collaborations is to have a data-driven path where you feed a model the data and it finds these complex interactions. And it's not just finding high-risk factors, it's giving you absolute thresholds. So it's immediately translatable to clinic. And not only absolute thresholds, but it's giving you a decision path. And the most important question now is, does this model, this simple model, does it maintain its performance? And it does. So here, this is the XGBoost model, 150 decision trees in concert with all the features. We're hitting high accuracy here, high area under the curve of the receiver operating characteristic. And again, this interpretable XGBoost model A single decision tree with 3 features is maintaining its performance. So what I would argue is, why just put out these complex models? Instead, let's work on improving their interpretability and maintaining their performance. And that's how we create some clinical impact. Now, that last project, I talked about diagnosing disease. So a lot of healthcare companies and academics are interested in diagnosis, but we're also shifting more to medicine 2.0, where we want to prevent disease. We're getting tired of just treating symptoms, but we want to prevent disease before it happens. This is a prognostic model for Alzheimer's disease, and it turns out that differentiating mild cognitive impairment from early stage AD is vital worldwide. And despite genetic markers like apolipoprotein and its E-form isoform, we have yet to identify patients at the highest risk of Alzheimer's disease. And I do want to clarify here for the audience that having these powerful models now that can, let's say, predict disease 5 to 10 years in the future, I'm not here to say that's all we're doing. Right? This isn't, I hope that folks are not concerned that, hey, these models are just going to tell you that, oh, you're going to get Alzheimer's disease in 5, 10 years. No, these work hand in hand with therapeutics. I think in the, just recently, Lilly came out with therapeutics for Alzheimer's disease, but they need to identify patients at the highest risk of developing AD before they develop it. And that's where the therapeutics and the pharmaceutical interventions work best. Okay, so we're not just predicting high-risk patients, we want to treat them. So this works hand in hand with therapeutics. Now, I tried the same strategy that I did before. Identify top 10 features, but you see the plateau here at 72%. And this makes sense because this prognostic problem is much more difficult than the diagnostic problem. You see that even for the same variable, the distributions are less divisive for this prognostic problem. And I do want to highlight that, again, if you're just taking a subset of your data, like here, just the top 10 features, they might be the most important features, but you miss out. You miss out on the interactions between these top features and the rest of the features. So it's quite important to consider the interactions of all your features together. And when we do that, when we look at all the different permutations and subsets of variables, we increase the performance by almost 20%. Same thing. We're not just sending out these complex models. We improve their interpretability and their simplicity and their scaling. And it maintains performance with the complex counterpart. Now, I do want to highlight here that XGBoost for this second project is recognized a comprehensive subset of features, over 11 features that are working in concert to predict Alzheimer's disease before it happens. I am only showing a snapshot of the features for IP reasons. But XGBoost included other things like race, ethnicities, years of education, visuospatial, delayed recall, motor skills, language. And this here is the state of the art for explainability. And the idea here is that we can assess for each feature the ordering of their importance based on these Shapley values. And then values here to the right indicate more AD risk, while values to the left indicate association with a control group. And the coloring indicates so the red coloring indicates higher values. So for example, here, higher hippocampus volumes are associated with the control group, while lower volumes are associated with the AD group. And this is well known in the literature. Again, you see the genetic predisposition. More genetic predisposition, you're at an increased risk of AD. Now, I do want to highlight this really interesting part here, this trail-making test part B time. And it speaks to cognitive processing, especially in executive function tasks that include task switching. And I certainly don't subscribe to the whole bilingualism increasing cognition. I think it kind of spawned from a flawed statistical study. But you can certainly appreciate that with bilinguals, they have maybe an increased ability in task switching because they need to switch between both their lexicons. And what we do notice is that, again, folks that are good at this task, um, you have better scores at this task are associated with the control group, and that bilinguals usually display initial AD symptoms around 5 years later than their monolingual counterparts. Another thing I wanted to say here is, again, it's so important to look at genetic factors in the context of other variables. Something like the apolipoprotein and the E4 allele is not exclusively associated with negative health outcomes. And in certain contexts, for example, I've read that it has some potential benefits, like improved cognition in younger individuals or potential protective role in certain infections. But the idea here is, I hope that we can appreciate the utility of state-of-the-art supervised machine learning, both interpretable and explainable components in clinical decision support and in preventing disease. And really looking at these variables, it gives you a better understanding of the disease and how it's manifesting. And it's almost like Alzheimer's disease is the brain going back to its infancy. Now, I want to shift gears and talk a little bit about commercialization in AI, how we can use AI to enable better research. This is RO, or Research Online, a company that I'm a part of, and it's meant to disrupt research worldwide, as it's the world's first platform to enable large-scale health research online. And it does this by picking up heart and brain signals from the participants' webcam. And the problem that it's trying to solve is research. And that research is expensive in time and money. And it's limited in participant recruitment and reach. And this results to research that is not generalizable and it has minimal translational impact. Now, the competitive landscape here in online testing certainly provides a powerful way to collect data, but it's limited to behavioral and subjective data. And to observe some phenomenon, like health and disease, certainly requires collection of physiological data. And this is a behemoth of a platform that we're growing, and it gives us hundreds of participants a day that we are capable of testing at 1/10 the cost. And it's you can conduct unitary studies to single clinicians that can conduct large-scale clinical trials. And we're decreasing the time in research, the cost, increasing the participant recruitment. So we have a large volume of data that's coming in, and also the reach. We are able to finally reach to difficult to recruit populations like women in clinical trials, infants. I'm not sure if any of you have tested infants before, but it's quite chaotic, and also patients and diverse groups. So here we are improving generalizability in research and the translational impact, but also improving AI, because with larger volume of data, especially looking at more abnormal cases that we can reach out to, covering more variability and heterogeneity in the population, allows us to improve our AI models. And this, all the data here is actually feeding forward into our own predictive tools for both terrestrial and spaceflight applications. If folks in the audience are interested in participating as a participant or as a researcher, please feel free to reach out to this email. We are currently my co-founder, Dr. Bara Al-Khazji from Kin faculty here at McMaster, her and I right now are conducting one of the largest exercise studies in the world. So it's very exciting to see how we can leverage all the engineering domains from optics to machine learning and bioinstrumentation with all the beauty in other domains like in kin and exercise science. I wanted to I just put this last minute because I did realize that I am focusing a lot on the transparency of AI. And I think it's super important that we have interpretable models that we can trust, and models that are that give you quantifiable explanations. I wanted to spend just a few minutes here talking about other important aspects to consider. So certainly the scalability and cost. I talked about some models that are more difficult to scale, and cost of having a machine learning platform. You have a few machine learning engineers and some infrastructure that could, that can run you over $1 million. I also want to emphasized the importance of human AI collaboration. This isn't about AI replacing anything, right? It's more about augmenting capabilities instead of replacing them. I want to highlight the importance of bias and fairness. It's quite important to have diverse and representative data, right? Ease of use, accessibility features, clinical validation. We want to ensure that models that we do in academia or in industry can generalize well to other scenarios. And we had a great comment last month with the speaker talking about ongoing monitoring. I've always talked to folks about their AI models, and they tell me they're actually not aware that they actually have to retrain their models. They just let the models go out and with no retraining or ongoing monitoring. And I think one of the most important parts too here is security and privacy. Instead of just focusing on building an AI infrastructure, you need to also build an information security and cybersecurity infrastructure. All right. Finally, I want to talk about this very exciting project here under the mentorship of Dr. Marie Pigier at PHRI. This is the microvasculature. These are the small blood vessels in our body, and they are indicative of the health of all organs. And we can see it non-invasively using retinal imaging. And historically, we've known for decades that systemic disease like hypertension manifests in the retina. And folks are getting very excited about the anatomical features of these blood vessels and how they relate to health and disease. For example, the diameter of these vessels, the tortuosity, the curvature of the vessels, and the branching complexity. The branching structure here follows an efficient design principle for delivering blood flow, and any deviations from that can compromise organ integrity. Now, recently, Google came out with this, where they showed the predictive capacity of these retinal images at large scale. Google predicted cardiovascular risk factors not previously thought to be quantifiable in retinal images, like smoking, your blood pressure, age, diabetes, gender, all can be accurately predicted through these retinal images. Now, going back to my earlier discussion, this is phenomenal, but for clinical utility, we need to start moving from explainability to interpretability. We need better quantifiable explanations of what's going on here, because these saliency activation maps are non-specific. And sure, it can show some anatomical features, but again, it's not giving us a quantifiable explanation of what these models are looking at. Our motivation for this project was that despite recognizing the utility of retinal imaging, we wanted to extract interpretable variables or meaningful variables in large populations. And we leveraged deep learning to quantify, but an interpretable form to quantify this retinal microvasculature. And we also wanted to see its association with clinical and genetic risk factors. Again, this is an important point for folks and entrepreneurs that are considering AI in healthcare solutions. Health isn't unitary. You need to consider different aspects and multimodal applications. Genetics and multi-omics and clinical data become quite important. So here we collaborated with the Vampire Group, and we were able to automate the process from segmentation to feature extraction. And instead of focusing on deep learning to predict, we can just focus on deep learning to segment. And then once you're segmented here, you can just apply some mathematical principles or some basic biomedical image processing to quantify the branching complexity here, for example, or the tortuosity or the diameters, okay? So this is an example, lower versus higher branching complexity. And what's very exciting is that the complexity of these small vessels is emerging as an early indicator of disease risk related to both the heart and the brain. Just some information on our data sources. Here we leveraged a national stratified random sample of 50,000 Canadians. Some of you might be familiar with the CLSA, the Canadian Longitudinal Study on Aging. And out of these 50,000 participants, 25,000 had retinal images. Out of the 25,000, we were able to extract this interpretable, meaningful branching complexity measure from 17,000 of these participants. And of these 17,000, 16,000 had genetic data. Now, another part of deep learning and AI is that, again, we're working with correlations, and it's in medicine and healthcare, we really want to start to establish causation. If folks are interested in genetics and AI and medicine, I definitely want you to reach out to Dr. Marie Pugier to get involved in some of these fascinating projects and the GML team at PHRI. Now, this is briefly Mendelian randomization here helps overcome confounding and reverse causation because the genetic variants here are randomly assigned at birth and act as a natural random RCT, or randomized control trial. So we are able to establish some causation with our variables. And I don't have time to go through many of these results, but just starting out here, this is lasso regression, so it's regularized regression. And we got branching complexity measures for an overall measure. And also we found differential results for the arterial and the venous side. And we see associations with cardiovascular risk factors, but we are also able to kind of point out that image quality is also playing a role in some of these prior deep learning models. So the exciting part here is that it's nice that we want to tackle some of the heterogeneity in medicine. And one way to do that is to start incorporating all these different variables. And machine learning does a great way of doing that. The takeaways from today is that we are certainly going beyond traditional statistical approaches in identifying high-risk factors. You saw that when you want to apply AI or machine learning in healthcare solutions, it's important to perhaps consider accessible variables. Without accessible variables, if they're difficult to acquire, then you limit the usage of your models and your variables. You saw the power here of absolute thresholds and this decision path. I thought it was quite exciting. And you saw that we can also improve the interpretability of models, but also maintain their performance. And I showed Row using AI to enable innovative research methods. And it turns out that it becomes a bidirectional relationship, that you use AI to improve research, you improve the amount of data and the quality of data that you get. And in turn, that improves your AI models. And finally, again, speaking now to the heterogeneity in medicine, it's important to leverage interpretable AI, imaging, genetics in medicine to clarify this interplay between risk factors, systemic health, and disease. I want to give a big thank you to everyone here for these projects. And I'm happy to take questions.
Awesome. Thanks, Mason. Excellent talk. I'll open it up for folks online who have any questions. Merrick.
Hi. Thanks so much, Mason. That was fabulous. You talked about, sort of cross-sectional diagnosis. You take a whole bunch of data and you make a diagnosis or a classification at that point. You talked about prediction. Is there any thought of using serial measurements for prediction? So, you may know the carotid IMT work where, you do yearly IMTs and you basically look at the progression of IMTs over time. I go to my dentist regularly. He tells me how bad my periodontal sort of gums are looking and all this sort of things. And, in medicine, we often use a tincture of time. You see a bit of a shadow on an x-ray and you say, let's repeat that at 6 months' time and see what's changed. So any thoughts on using, rather than single time prediction, using multiple and using the slope of change as your predictor?
Yeah, that's an excellent question. Absolutely. And this changes from a cross-sectional design to more of a time series problem. Absolutely. The idea there too is these cross-sectional studies are great because we want to capture disease risk, diagnostic or prognostic, at the earliest possible time. So I think they're still quite powerful. But in your scenario, the only thing you want to be careful of is the collinearity, right? So if you're capturing data at a single point and you're capturing it multiple times, machine learning still has issues, again, even more so traditional stats, in the collinearity between variables. You have a lot of relationships between variables. And what you said too is an excellent point, that you can actually look at the change or the rate of change between, let's say, the first and the second visit. As long as you take care of collinearity, you can look at time series classification problems. And this becomes quite interesting because you can, folks now, they're, I'll refer you to a Nature Biomedical Engineering paper using the Shapley values where they have intraoperative time series classification. So during the surgery itself, you have folks that will, models that will indicate levels of hypoxia during that surgery itself. And that becomes very useful. And that's actually, this is our next step for this project, is that we look at the change in these branching complexity for this specific project.
Mason, I'll ask one while we're waiting. So I'm referring to your recent work analyzing the retinal images. So presumably those were captured, across, is this a national database?
It is.
Okay, so they were captured from like many clinics using many different machines across many patients all at different times. So there's going to be a lot of, I'll call them biologically irrelevant features captured in these images just because they were gathered at different times by different people, et cetera. And as training an image classification model from images that are acquired on different machines at different times by different people introduces a lot of noise into your model. So how did you go about removing that noise prior to training?
Yeah, no, I don't usually say great question, but that was a great question. Now, I do want to highlight here that we leveraged a Vampire Group. So this is a famous group that focuses on these retinal images. So we just got the extracted features. Now, you mentioned a very good point that, we certainly don't want these models to make accurate predictions based on the wrong reasons. And there's a lot of heterogeneity in many devices, many data acquisition systems, many medical images. And the problem, too, is the image reconstruction in devices is intellectual property. So we have no idea how these devices are actually reconstructing the images from one MRI to the other, from one ultrasound to the other. And another excellent point is that, that operator variability. So a lot of, especially with these retinal images, perhaps you have some of the operator variability that that's coming up too. Now, that's exactly some of the problems that we're dealing with now. How do we, we're dealing with issues with these images where perhaps maybe one image is a bit more overexposed than the other, right? So you have a lot of that variability there. In one hand, that's certainly a problem where we want to create maybe more interpretable models to ensure that we are predicting and using the right pixels or the right features. But in another sense too, is it might be nice to also pick up on that heterogeneity. We want data from different devices such that we can hopefully bypass the noise in the data and pick up on more relevant cues. And I think if we keep focusing on more complex models rather than interpretable models, that yes, we're always going to start picking up on the noise instead of really on these specific features and variables.
Thanks, Mason.
Thank you.
I'm going to open it up to the floor. I have a ton of questions, but I don't want to hog the mic. Okay, I'm going to ask one out of selfishness. So, it's very obvious, from an AI practitioner's perspective, that interpretable/explainable models are required to facilitate, I'll say, trust when healthcare practitioners, let's say, rely on these models to help them make diagnostic or treatment decisions, whatever. And as you were alluding to earlier in your talk, simpler models are far easier to understand than large, sophisticated, neural network based models, let's say, deep learning algorithms. And I just want to the way you interpreted or the way you explained something, I interpreted, but I want to make sure I captured it correctly. So there's this field in AI called knowledge distillation, right? It's where you have a remarkably sophisticated model that is able to make, some predictions for something, right? But if it's really complicated, we don't actually know what the model has learned and how it's making those predictions. So you train a much simpler model, to make very similar predictions. And that simpler model is, easier to train, easier to interpret, et cetera. So that's called knowledge distillation. Is that sort of the idea that you were discussing during the first part of your talk, or did I misinterpret?
Yeah, it's aligned with that idea. Now, something like Shapley values and even Lime, they do that, right? So Shap here, you can apply it to more complex models, and you can get an understanding, right? An understanding of how these features, for example, are using, or how the pixels are contributing to the final decision process. Now, the emphasis here, though, it's even when we're creating, let's say, an explanation of that complex model, sure, we get an idea of some of its workings, or it might be more of an accessible explanation to end users. But the problem is, we don't still fully understand the decision process compared to something like a decision tree. So what I argue here is that these traditional machine learning models, these gradient boosted ensembles, can be high performing and are inherently interpretable. We understand every part of that decision process. So again, it's a bit more trustworthy than, of course, using something like SHAP, where it gives us accessible explanations, but again, we're still not there yet.
Thank you, Mehdi.
Thank you for the talk. I enjoyed it. I wanted to, it's not exactly a question, but it's kind of like a follow-up to what John was asking to. In this final project, you were explaining how you use deep learning to get to that model of the microvasculature, and then from there you have you're using geometry and our context knowledge of how those need to be to get to the metrics that actually are used for detection or disease diagnosis. I just wanted to highlight that that's actually less sensitive to the kind of variations that John was saying. So, meaning that the final decision here is not made on the basis of simple comparison of pixel intensities in a black box, but the neural network is used essentially to facilitate extraction of those measurements that are known predictors of the disease or identifiers of the disease. And I like it this way in the sense that, and I see this the right way to go in most scenarios where deep learning or AI comes in to kind of like do the segmentation or essentially convert the image into components of that are important and relevant. But we don't just throw out all the context of knowledge of what we know about the disease to have a black box that image comes in and diagnosis goes out. If we use AI to, although that's also one, that can also be an additional method of like a parallel method or on part of the ensemble, but getting AI to get to the point where you can actually do the measurements and see if the known identifiers of disease are there is, I think, helping with interpretability and explainability and also performance, I think.
Nicely put.
Thanks, Mehdi. Anybody else? We have time for another question or two. No, I'd like to, thanks, Mason, for a lovely talk, very illuminating. You covered a lot of ground. So thank you for that. And I will, before we all leave, I just want to let everybody know our next healthcare rounds will be on November 15th. So keep an eye open for forthcoming announcements about that. So thank you, everybody. Thank you, Mason. I hope you enjoy the rest of your day.